Okay, this is going to be a direct response video to the following claim by Draftscience. I'm going to respond with real physical evidence as counter evidence with actual data. All right, so I've already done this. I've made a half-an-hour video with all of my data collection proving you wrong, essentially, that your model fails all over the place, also within a Newton's cradle. But yeah, you haven't responded to it. So what I'm going to do now is I'm going to make a direct response video, right, by playing a clip, a part of your clip where you make your claim. So let's play your video and then respond with real counter evidence.
Physicists still say that. Professor Lewin's rather famous for saying nature can deal with kinetic energy one way or the other, but nature can't finagle momentum. That momentum is foundational. All right, and I would clearly argue that it's true of a Newton's cradle, a purely elastic collision where nothing deforms, energy isn't dispensed with through heat or other movement, that the substance of the energy stays in the system, and the two objects always have to possess the energy, whatever it is, the movement. So you start with 100 in, okay, a light object hitting a one mass object hitting a three mass object. Start with the 100 comes in, and there's people saying that it's possible that this leaves with 150 momentums.
Not only people saying it, but also all the evidence is saying it. All the experimental results are saying it.
Assets. And that this leaves with 50. And that somehow this 50 is in this direction, and so that undoes the 50 in this direction. Yep. But the fact is that you have 100 in, and now you have 100 plus 150, you have 200 things moving in the universe. So only one thing was moving in the universe, going 100. Now you have two things with a total of 200. So you've made free movement in the universe.
So that has always been your problem. You treat both sides, even though they're opposite direction, you treat them as positive values, and so you add them together, and that always, for every experiment, for every air track experiment, for every metal track experiment, for every Newton cradle experiment that I'm about to show you, that always produces way much more free extra momentum if, of course, if you're going to treat them both as a positive value. But if you're going to treat one direction, the opposite direction, as a negative value, then your error percentage, right? Your error percentage is going to be a lot less. It's going to be a lot more closer to the initial momentum. So, which is a clear sign that you have to treat the opposite direction as a negative value, or else you're always going to end up with so much more free momentum, and therefore literally every air track experiment, every metal track experiment with Pascal cards and Vernier cards, and every Newton cradle experiment, they all must be broken in some way, or be deliberately manipulated, forced to come out the kinetic energy way. Now, do you really think, you really believe that?
That can't happen.
It happens.
You can make it happen in some other experiment. Well, I still say you can't. But anyway, the real argument is what do we know from Newton's cradles is that you don't do vector math, you don't do subtractions and addings.
Yes, you always have to do it, otherwise you end up with so much more free momentum.
Addings. All movement counts. You can't make something go left and that's anti-energy, and something going right is positive energy. There's no positive and negative. So the consequence of the Newton's cradle is that it forces the energy back in. So this free momentum you made is now going to come into the experiment. Now you got an experiment. We got 50 coming in from one side, 150 coming in from the other side. And they are arguing that somehow the 50 does cancel with the 150 and you only get 100 left. Now I'm saying that's impossible. It doesn't happen.
It is possible. It always happens. I'm going to show you in a minute.
Cradles don't work that way. If I have 50 coming
in, they do.
150 coming in, I'm going to get 200 out. It has to be 200 out, not 100.
No, so again, 150 coming this way, 50 coming this way, and then after reflection, this one should leave with 200, but I'm going to show you, no, if we are going to treat it as in this way, no, if we are going to apply your model, then you're always going to lose so much more momentum, which I'm about to show you. It's never the combined momentum. You will see.
Newton's cradles can't destroy momentum.
All right, so let me just show you right away. So I have 6 cases, 6 examples, which are going to prove you wrong. This is the first one. This is my own setup. All right, this is my own setup. Now what I'm going to do is I'm going to make a PDF file of each one of these runs. And then I'm going to put it on my drive, and I'm going to share the link because you can see how I measured it. So I put a ruler underneath the balls so you can see the exact location. And then 2 frames later, you can see how much the displacement is. Then you can calculate the velocities. You can also see the timings. All right, so, and over here, then 2 frames later, it's 7 milliseconds later. All right, so which means you're going to have to divide the change in distance by the change in time, so you can calculate it for yourself. But now I'm not going to go over it. I'm not going to go over every single individual print screen. Let me just show you the results. All right, so these are the calculations. But this is the case where, right, the 1 mass is coming in and the 3 masses coming in simultaneously, right? So the 50 momentum and the 150 momentum, and then after collision, this one is going to stay stationary, and this one is going to leave with, well, according to Draftscience, it's going to leave with 200 with the combined momentum before collision. But the evidence says no, you have to subtract. You don't have to add those momentum together. So let's see. So according to conventional science, all right, so this one came in with a negative momentum, this one came in with a positive momentum, and so the combined momentum is 6.96. So this one should leave with 6.96 momentum, but it only came out with 5.83 momentum, which is a loss of 16.23%. According to Draftscience, we treat these both as a positive, which means we have a total momentum before collision of 11.24. But it only left, so yeah, so it should have been leaving, it should have left with 11.24, but it only left with 5.83. And those are the measurements. You cannot deny it, right? So which means we have lost 48.13%. Right? Let's go to the next case. This is also my experiment, my second test. So according to conventional science, right? So we treat one side as negative and the other side as a positive. The total combined momentum before collision is 6.9. So this one should leave with 6.9 after collision, but it left with 8.28, which means we have an increase of 19.9%. All right. So that's the error percentage. For Draftscience, the total combined momentum before collision is 15.74, but it only left with 8.28, which means we have lost 47.39%, right? So we can already see a pattern. For conventional science, the error percentage is about 20%. For Draftscience, it's around 47 to 50%. Next, this is the same video of the 1 to 3 mass, right? This one, the one that Lexa analyzed, and the one that Draftscience came up with. So according to conventional science, the total combined momenta is 5.15, and after collision, the small one left with 6, which means there's an extra of 16. Hold on. No, it should have been, yeah, it should have come out with 5.15, but it came out with 6. So we have gained, sorry, there's a lot of traffic noise. I hope it's not too disturbing. So we have an extra of 16.5 of 50%. The error percentage is 16.50. Again, the same pattern. For Draftscience, the total momenta is 12.85, but it only came out with 6, which means we have lost 53.30%. You see the pattern, right? The error percentage for Draftscience is around 50%, and for conventional science around between 50 and 20. Right? The next one. The next one. So this is still the same experiment, okay? So they keep doing this. The one comes in, then they do this, and then up. So we have the same runs over and over again. So this is now the second run of the same experiment. The combined momentum, according to conventional science, is 5.14. But this one left with 4.10, which means we have lost to 20.23%. According to Draftscience, the total combined momentum before collision is 10.28, but it only came out with 4.10, which means we have lost 60.11%. right? The third run. Right, so the total combined momentum according to the conventional science is 5. And so the small one, the one mesh should come out with 5 momentum after collision, but it only came out with 4.10, which means we have lost minus 18% of momentum. According to Draftscience, the total combined momentum before collision is 10. So after collision, the small mesh should leave with 10 momentum, but it only came out with 4.10, which means we have lost 59%. Now the last one, according to conventional science, the combined momentum before collision is 3.42. So the small mass, the one mass should leave with 3.42 after collision, but it left with 3.85, which means we have an increase of 12.57%. For Draftscience, the combined momentum before collision is 6.84, but it only left with 3.85, which means we have lost 37.42%. Now, this is the lowest error percentage for Draftscience model, 37. All the others were 50 to 60%, right? And for conventional science, the error percentage was around between 12 and 20%. So this is a clear pattern, right? Draftscience model always consistently creates a higher error percentage. Right? This is what the evidence is pointing out. Now, for the case where we have the 3 mass stationary, the 1 mass is coming in, right? So let's say it's coming in with 100, right? Then reflection, and then, right, so this one, after reflection, this one should be treated as a negative, and then if you have the negative plus the positive, right, that should equal the initial momentum. According to Draftscience, you have to treat also this one as a positive and positive. But if you do that, it's going to end up with a lot more free momentum. So we have the mass 3 stationary. Again, 6 examples. So again, this is my test, my setup. Hold on. So let's see. So before collision, yeah, so this one is stationary, the mass 3. The one mass came in with 5.75 momentum. After collision, the one mass reflected with minus 3.25 according to conventional science, right? Minus. And then the 3 mass lifts off with 9.50. So the total combined momentum for conventional science is 6.25 if you treat it as a negative value, right? And the initial momentum was 5.75, which means we have gained 8.69%. That's the error percentage. Now for Draftscience, we have to treat them both as positive values. So that would be a total of 12.75, but the initial momentum was only 5.75, which means we have an increase of 121.73. Yeah, 121.73%, which is an insanely high increase of extra free momentum, right? Now let's go to the second one. There we go. My second test of my own setup. The initial momentum was 10, and the total combined momentum after collision for conventional science, all right, would be 11.5. So, and the difference between the total momentum after collision and the initial momentum is 15%. You have an increase of 15%. For Draftscience, if you treat them both as a positive value, the total combined momentum after collision is 22.1, which means we have an increase of 121%. 121% of increase. An increase of 121% of free momentum, free energy. I mean, come on. Isn't this so clear already that this can't possibly be working? This is the third example. So the initial momentum was 5.71, and the total combined momentum after collision, according to conventional science, is 5.57, which means we have lost minus 2.45%. According to Draftscience, the total combined momentum before after collision is 9.85, which means we have gained 72.50%. Do you see the pattern? All right, next example, the second one of the same experiment here. The initial momentum is 4.57. The total combined momentum after collision, according to conventional science, is 4.2, which means we have lost minus 8.8%. According to Draftscience, the total combined momentum after collision is 8.8. All right, and initial momentum was only 4.57, which means we have gained 109.52% of extra free momentum. Damn. So much more free momentum. Next run. The initial momentum is 4.42 momentum, and the total combined momentum after collision, according to conventional science, is 4.29, which means we have lost 3.11%. According to Draftscience, the total combined momentum after collision is 7.71, but the initial momentum was only 4.42, which means we have gained 74.11%. Wow, so much extra momentum. All right, the last one. The initial momentum was 3.85. The total combined momentum after collision, according to conventional science, is 4.8, which means we have gained 24.67%, which is, I guess, the highest error percentage for conventional science. For Draftscience, the total combined momentum after collision is 7.8, but the initial momentum was only 3.85, which means we have an increase of 102.59% of extra free momentum. Done. All right, can you now see how your model fails all over the place? How each time in this situation where the one mass is coming in, colliding against a heavy mass, right, and after collision, if you treat both directions as a positive value, that you end up with an average of 100, or so it was between 70% and 120% increase of extra momentum each time. It happens within an air track, whether it happens in an air track or a metal track or a Newton's cradle, it's always the same thing, right? If you're going to treat both directions as positive values, you gain 100% of extra free energy. All right. Now, if you still claim that you shouldn't be subtracting it, all right, that you should treat them both as positive values, right? If you still claim that, then how do you explain this? All right. Are you still going to say, well, it must be broken? The experiment must be broken. Even the Newton's cradle experiment must be broken in some way. It must have been deliberately manipulated. Okay. If you still claim it, then show me some real physical evidence where it comes out your way. And even though if they are done badly, do you really think if we're going to adjust, all these stupid little details, that somehow we're going to decrease this 100% to 0 or to 20%? Do you really think you're going to be able to decrease the error percentage with 80%? I'm sorry, but clearly this can't possibly be the case. If you treat the opposite direction as a negative value, you get a lot closer to the initial momentum, which is a clear sign that, yes, we might have to treat it as a negative value, the opposite direction. Otherwise, we have so much extra momentum. All right, that's it. Till the next time.